I am going to explain how to use the ICE table in order to calculate the pH of a weak acid. So first, when the question is given, calculate the pH of 0.015 molar of HCN, we need to double check that the given acid is strong or weak, because as I mentioned in my previous video, a strong acid, its pH will be calculated in a different way. Now this HCN is a weak acid, so when it ionizes, it's not going to fully ionize. It will partially ionize into a small portion of hydronium ions, H3O plus, and CN minus, the cyanide conjugate base. In this case, I am not able to say that this 0.015 molar is completely equal to the concentration of H3O plus, and this is why here we need to do the ICE table in order to see how much of this molarity given to us is going to form H3O plus. I stands for initial, C stands for change, and E stands for the equilibrium established. So at the beginning, initially, we have 0.015 molar of HCN. Liquid H2O, we do not consider it. And first of all, we don't have any H3O plus formed or CN minus formed. The change is the ions that are going to ionize. So it's the quantity consumed from HCN in order to turn into H3O plus and CN minus. So under the given acid, we write negative X because this is going to be lost because it is formed in form of ions. And here we put plus because they appear, they show it's ionized, it is formed. So at equilibrium, the remaining concentration of HCN is the initial concentration minus, you subtract from it the ionized quantity, and for H3O plus, it is the quantity ionized. So this is called ICE table. Now, after doing the ICE table, we write the formula of the Ka, the ionization constant of this acid, which is equal to the concentration of H3O plus multiplied by the concentration of its own, of the cyanide minus, CN minus, over the initial concentration of the acid. Now, because this is a weak acid, we will have a given Ka. If in the question you don't see a given Ka, this is most probably because the acid given is strong. So if we substitute 4.9 times 10 to the power negative 10, the concentration of H3O plus is X and of Cn minus is X. So it becomes X squared divided by 0.15 minus X. When we reach this step, there's a very important assumption that we need to do in order to continue with our calculations. Now, since the value of Ka is very small, we assume that the calculated X is going to be a very small value. Assume that X is very small, and in this case, 0.015 minus X is going to approximately stay the same. So when we do this, we make our calculations much easier. So X squared over 0.15. Therefore, X is equal to square root of 4.9 times 10 to the power negative 10 multiplied by the initial given concentration. In this case, I'm going to get you the answer, times 0.015, square root the answer. The calculated X is 2.7 times 10 to the power negative 6, which is indeed small. Now, before we continue our calculations, since we did an assumption, we need to prove that our assumption is valid. So we do what we call the 5% rule, in which we divide the calculated X over the initial concentration multiplied by 100, and it is called a 5% rule. If the answer we obtained is less than 5%, then our assumption is valid. So this number will give me a value of 0.018, which is in really less than 5%. So my assumption is valid. And now I can say that X, which is equal to the concentration of H3O plus, equal to 2.7 times 10 to the power negative 6 molar, is the concentration of H3O plus. From there, we need to do the last step, which is calculating pH. pH is minus log the H3O plus concentration, and the final answer will be 5.56, almost 57, pH equal 5.57.